Right, so today is Wednesday, so Monday you took your exam, so let's go all the way back to last Friday. And last Friday we mentioned some important equations here. One is the equation for an acid. Okay, so here we have some acids for you. The equation that I'd like for you to remember is an acid will react with water. Okay, any acid. And this is an equilibrium. Okay, this is an equilibrium. We studied equilibrium. You had test questions on it. An acid will give away a proton. Okay, this proton is called H+, and it will give you H3O+. This is called hydromonium ion, but I'm also, the way I'm teaching it to you guys, you'll also see me referring to it as straight up H+, and then A-. Okay. All of these are in water. Water is a liquid. Okay. So here we have a K, and this is, I'm going to call Ka. Okay, the A stands for acid, and it's products over reactants. All right, so this is an equation that I'd like for you guys to know. Okay, and we have some examples for you here. So there's something called pKa. Okay, you'll learn about this if you ever take biochem or organic chemistry. I know we teach this in biochem, or actually, yeah. Okay, biochem. So pKa is minus the log of Ka. This lowercase p stands for power. Okay, power, and it's the minus log of whatever you want to take of. So the relationship is this. Okay, if you have a large Ka, okay, you see the magnitude of this Ka. If it's very, very large, imagine if it's 1 million, or let's say I give you $1 million. Okay, you're moving forward. Okay, the reaction is facing forward, moving towards the product side. Okay. Now, because of the pKa, the power of the pKa minus the log, this just means your pKa is down. Okay, like pH. If your pH is low, you're more acidic. If your pKa, if your pKa is low, that's a really strong acid. When I say really strong acid, it's really good at giving off proton H+. Okay, it's really a good source of H+. It really is a good source of H+. Okay, so this is what we'd consider a really good acid. Okay, the stronger the acid would have what? A larger magnitude of Ka and a lower magnitude of pKa, just simply by the way the minus log math works. Okay, just simply by the way the minus log math works. The lower the value of this, more acidic. The higher the value of Ka, more acidic. Okay, so if you were to rank acids on any quiz or any exam, okay, you're looking for the higher value of Ka, or on the flip side, the lower value of pKa. Okay, that's just how it works. Okay, kind of like pH. Okay, what is more acidic, a pH that's 2 or a pH that's 5? Okay, the lower value of pH is more acidic. Okay, so more acidic. Okay, more acidic. Okay, we also can do the same thing to a base. But before we do that, just remember here, this is the acid. Here, water is acting as the base. And this base is conjugate, or is paired up to this conjugate acid. So these two are a couple. Okay, they're a couple. And this acid's conjugate base is this guy, A-. So HA and A- are a couple. All right, so check out some of these acids here. All right, so we have HCl, and this is the equation. Okay, the equation for Ka, and look at that value. Okay, usually the Kas are at a very specific temperature, so I think I got these at 25 degrees C. But look at that, 1.3 times 10 to the 6th. That's huge. Okay, Okay, that magnitude, remember there's no units here. These are unitless. Okay, that number is huge, so that's going to very much favor the products, and you'll get a lot of H3O+. Okay, and your pKa is very, very small. Okay, notice it's going all the way down to the negative numbers, minus 6.20. Okay, what would be a weak acid here? Probably this one. Okay, look at this Ka for this one. 5.8 times 10 to the minus 10, that's NH4 plus. Okay, look at the equation. Okay, and the pKa is 9.24. Right, so this would be a very weak acid, a poor source of H plus, whereas HCl would be a good or a poor source of H plus. Okay, hydrochloric acid. Okay, obviously it's a good source of H plus acid. Okay, it's in the name, hydrochloric acid. What other acids do you think would be pretty powerful? Okay. There's HSO4 should have a minus sign by it. Nitric acid, okay, this seems to be pretty strong. 2.4 times 10 to the 1. 1 times 10 to the second, 1 times 10 to the third is sulfuric acid. Okay, all these large values of Ka mean it's a good acid. What about water here? I think water is a good source of H plus. Okay, 1.0 times 10 to the minus 14 is the K. It's actually called Kw, and the pKa is 14. Okay, so the higher the value of pKa, okay, the poorer, I can't use that word. The poorer it is as an acid. Okay, the lower the value of the pKa, the better the acid is. All right, same thing for the base. All right, same thing for the base. Let's do that really quickly here. This is what I want you to know. Okay, so the base is going to abstract. The base will take that proton. Okay, this is the base. Brunstad base is what we'll call it. And then this will give us HA aqueous plus OH minus. Okay, aqueous. Okay, this will have a KB. And that's the same thing, products over reactants. All right, so here, unlike the acids, the counterpart, an acid is a good source of H3O plus. Okay, the base is a good source of OH minus. Okay, the base is a good source of OH minus. And then, like before, the power of Kb, pKb, tells us how good of a base it is. It's just the minus log of Kb. And the way this works is if your Kb is really large, that means this equilibrium is favoring the product side. Very large. Imagine if you had $1 million. Okay, you're moving forward. Okay, if this Kb value is 1 million, okay, it's moving towards the products. Just by the way the minus log of the math works, okay, the pKb is down. Okay, pKb is down. Okay. So these are the things that tell us what is more basic. Okay, you look for the higher Kb. Okay. Kb, okay, you're looking for OH minus. Anything that gives you OH minus. Okay, any acid. Ka is anything that gives you H3O plus. Okay, I'll highlight those in green. Okay. Ka, something that gives you acid. Kb, any equation that gives you OH minus. Okay, I do not know if we derive this equation here, but I'll go ahead and tell you it. There is a relationship between Ka and Kb. Okay, and then that is Ka times Kb is going to equal to Kw. So that's another relationship that we should know about. Ka times Kb is equal to Kw. Okay, what is Kw? Okay, it's 1.00 times 10 to the minus 14. All right, that's Kw. What is the chemical equation that represents Kw? Okay, what equation is that? Okay, the W stands for water. Okay, so the equation is this, H2O. Okay, it's water doing acid-base chemistry on itself. So here, this water donates a proton. This water takes the proton. Okay, so this takes the proton. This is the base. Okay, this water gives off a proton. It's an acid, so water can have acid-base properties. That's a very fascinating thing in the biochemistry world, or other chemistry worlds. This water takes a proton. All right. So when this takes the proton, it becomes H3O plus. So this would be the conjugate acid. And then when this donates its proton, it becomes OH minus, the conjugate base. Okay. So this is the Kw reaction. We'll add H2O plus H2O together to give you 2H2O. And this is Kw. Okay, which at 25 degrees, which is something that you guys should know, is 1.00 times 10 to the minus 14. Okay, this is quoted at a specific temperature, so this temperature here is 25 degrees. Okay, it's still unitless, as all equilibrium constants are unitless. All right, so Ka times Kb is equal to Kw. Okay, pKa, okay, plus pKb is going to equal to 14, and then pH, the power of the hydrogen ion concentration, plus the power of the hydroxide ion concentration will also equal 14. So there's a lot going on here in terms of acid-base chemistry. Okay, all of this really underscores the point of how strong an acid is and how strong a base can be. How strong an acid is, how good is it in giving you H plus. How good is it in giving you H plus. Okay, that's the power of hydrogen ion concentration, pH. Okay, now how good is a base? Okay, if I give you a chemical, how good of it is a base? Well, how good a base it is really depends on how much hydroxide ion it gives off. Okay, that's measured by the power of OH, POH. Okay, all of that comes together. The sum is 14. All right, so here's a table here. Okay, so we do not memorize Kas and Kbs. You don't have to memorize all this stuff, but here's some bases. Okay, so let's look at some bases together. Okay, Cl minus, is that a good source of OH minus? Okay, what do you guys think? 7.7 times 10 to the minus 21, is that a good source of OH minus? Okay, no. Okay, that number is very small, 7.7 times 10 to the minus 21. Okay, so is chloride ion will give you OH minus in water? Okay, is it good? Okay, no. Okay, why is it not good? Okay, the value of this Kb is just so small. What's a good base here then? Maybe this one, phosphate. So phosphate may be a good source of OH minus, because phosphate can react with water, giving you hydroxide ion, and the Kb for that is 0.0238, okay, with a pKb of 1.62. So that could be a good source of OH minus. Okay. So just as before, another thing I want you guys to know, we want to emphasize this. Okay, the higher the Kb, the better the base. The better at that chemical in giving you hydroxide ions, and by nature of the math of minus log, the lower the pKb. Okay, this is the rules that govern basic. Okay, what's a good base? Okay, the best base will have the highest Kb, and the lowest pKb. Same thing with Kas, same thing with pH. This is another poor base. Okay, what's another poor base? Okay, sulfate is not a good base. Okay, it does not give you good OH minus, because 1.0 times 10 to the minus 16. Hydrogen sulfate, okay, hydrogen sulfate, HSO4 minus, is not a good source of OH minus. Why? Because the Kb for this reaction, reacting with water, is 10 to the minus 17. Okay, not good. Okay, not good bases. All right, let's go to page. Let's go to page 7 in our notes. Okay, 7 in our notes here. All right, can we know this? Okay, what something is basic, what does it mean? When something is acidic, what does it mean? When something is neutral, what does it mean? Okay, this all has to do with whether a solution is more on the acidic scale or more on the basic scale. Okay, if it's more on the acidic scale, obviously there'll be more H3O plus proton than OH minus. So that's an acidic solution. Okay, this pH would be less than 7. Okay, the power of the hydrogen ion concentration. Okay. What about the opposite situation where something is more basic? It's also called alkaline. When your OH minus concentration is greater than your H plus concentration, that's basic. The pH scale would have this greater than 7. Okay? And if the concentrations of acids and bases are equal, the pH would be 7. Okay, what about pOH? Okay? In a neutral solution, the pOH would also be 7. Okay? Plus, because pH plus pOH is equal to 7. In an acidic solution, the pH is less than 7. The pOH would be greater than 7. Okay, whatever it does so that the sum is equal to 0. And in a basic solution, if the pH is greater than 7, the pOH would be less than 7. Okay. And then a couple of math equations. We went over this last Friday. So, on the exam, make sure, and we'll do some practice problems here, make sure you're able to go back and forth. Okay, if pH is minus the log of the hydrogen ion concentration, okay, if I give you the pH, for example, in a math problem, okay, how would you get the hydrogen ion concentration? Okay, you do the anti-log. Okay, the anti-log is 10 to the power of minus pH. The power of the Ka, this equilibrium constant, is minus the log of Ka. Okay, on a math exam or a chemistry exam, if I give you the pKa, how will I get the equilibrium constant? Okay, the Ka, if you want to go back, is going to be the anti-log, which would be 10 to the power of minus pKa. So we'll do these types of problems in our example set. Okay, so making sure we can go back and forth between one or the other. All right, we'll talk about this in chapter. Okay, in our next chapter, chapter 16, we'll talk about this, but there's something called percent ionization. So just remember it for now and store it later for our chapter when we talk about solubility products and all that stuff, weak acid, strong acid. The percent ionization, okay, you're going to take your hydrogen ion concentration and divide it by the initial concentration of the acid, and then you'll multiply it by 100. Okay, so this hydrogen ion concentration you'll get from the ice table. So we'll have a lot of ice tables in our next chapter. And then this is the concentration that is in the problem. Okay. So if you don't understand this now, don't worry about it, but this percent ionization is going to be important. Okay, how good an acid, HA, in giving us, in dispensing, in producing H+. Okay, we take that fraction, we multiply that by 100, and this tells us how good that acid is in giving off or being a source of H+. You take the H+, divide it by the acid identity, the actual acid concentration, and that tells us how good that acid is in giving us protons. H+ is the acid proton, and then the acid is whatever acid it could be. Okay. So let me tell you this now. It's a good opportunity. First of all, we'll study this more deeply in chapter 16, so if you don't understand it, that's okay. But 100% ionization. Okay, what does that mean for it to be a 100% ionization? Okay, it means that nearly all the HA goes into what if it's 100% ionized? If it's 100% ionized, nearly all the HA becomes H+. Okay? It's 100% ionization. Okay? So like that, there's 6 acids that we should memorize, okay, that do this. Okay, they're super strong. Okay, they're very strong. Okay, so these 6 acids it'll give us 100%, that is full H+. Okay, these 6 strong acids are they will give 100% ionization. Okay, the first one is HCl. Okay, this is not 50% or 75% or whatever. This is 100% or 99% ionization. Okay, that's hydrochloric acid. Okay, another one is HNO3. This is nitric acid. If you have a bottle of nitric acid, that's 100%, close to 100% H+. Okay, it's a powerful source. That's why these are very dangerous to work with, because it's just so acidic. Okay. Another one would be H2SO4. Okay, this is another strong acid, 100% ionization. Okay. Another one would be hydrobromic acid. Okay. All right, another one would be hydroiodic acid. Okay, these are the 6 strong acids. And then finally, I don't know if you know this one or not, this is perchloric acid. Okay, perchloric acid. So this is, do you know the names of these? Okay, hydrochloric acid. Okay, nitric acid. This is sulfuric acid. Okay, this is hydrobromic acid. All of these will give you 100% ionization. Okay, this is hydroiodic acid. 100% ionization. So let's do an equilibrium reaction with sulfuric acid. Okay, let's do an equilibrium reaction with this. What would the Ka be for this? What would the Ka be for this acid, HCl? Okay, let's write that here. Okay, it's going to be HCl, okay, on an exam, okay. Question would be, what is the Ka for what's the Ka chemical equation for hydrochloric acid? So you take that acid, okay, what will it react with? Okay, water. Okay, what do acids do like hydrochloric acid? They're going to give that H plus proton away. Giving you H3O plus, and what's the conjugate base for hydrochloric acid? What is its conjugate? Okay, what will it be? Okay, this gives off the H plus, H3O plus, yep, Cl minus. Okay. But this is a strong acid. Okay, because it's a strong acid, bless you. Okay, I am going to put the arrow one-sided. Okay, one-sided. Okay, why did I do that? Because it's a strong acid. So this is what we mean by 100% ionization. Okay, very little goes back. This is not an equilibrium. This is 99 to 100% moving forward. It's going to be like that for all 6 of these strong acids. Okay? If it's not one of these 6 acids, then it's an equilibrium. But if it is one of these 6 strong acids, it's going this way. This is what we mean by a 100% ionization. Okay, what would the arrow be for something like, I don't know, nitric acid? If you were to ask the equation, chemical equation for the Ka of nitric acid, it will be the same thing. What will the arrow be? Will it be an equilibrium arrow, or will it be an arrow that goes straight? It will be an arrow that goes straight because it's a strong acid. This is one of those things that's going to be 100% ionized, not 50%, not 33%, not 75%. 99 to 100% ionized. The conjugate base will be NO3 minus. So if you have a bottle of hydrochloric acid, if it's very concentrated, if it's super concentrated, that's just all protons, very concentrated. Usually what we do in the lab, like you've worked with it in the lab, we dilute it to 6 molar, 3 molar, some lower concentration. But these things are very nasty. Okay, if you work with them, like in a fume hood, and put them in acid containers, so on and so forth. These are strong acids, 100% sources of H plus. Okay, so make sure you know your strong acids. At least know them come the 3rd test, which is a couple of weeks away or whenever it is. All right, so page 8 here, we have a pH meter. Hopefully our pH meters are working. We had some issues with the pH meters in the lab. So there's also something called pH paper. How many of you have heard of pH paper? Okay. Is that a mosquito? Okay. pH paper, litmus paper, okay, all those things. So these things are very sensitive to the pH, okay, and they'll change color based upon the acid concentration or the OH minus concentration. So everything has a pH, okay, everything, Your stomach acid is very acidic, gastric juice. Everything biological, they even have blood pH. Tears have pH. Household ammonia is very basic, 11.5. Okay? Everything has a pH, which also means everything has a POH. Okay? Because pH plus POH is equal to 14. Saliva, urine, blood, lemon juice, vinegar. Okay? So, which means all these substances, whether they buy them at Walmart or whether they're found in the body, has some sort of acid component. Okay? Has some sort of acid or base component to it. Okay, it's measured using a pH meter. And what are the units of pH? Okay, are there units of pH? Okay. Since pH is a scale, will we have units? Okay, there are no units. Okay, so just as a reminder, pH, POH have no units. Okay, what in this class have we studied so far that has no units? pH, POH. This should be good, right? You don't have to worry about units. I don't have to take, your mean professor doesn't have to take off points because you don't have units. Okay, these are unitless. pH, POH, which is a scale. Ka, which is an equilibrium constant, has no units. Kb for the base has no units. What else? Kw, the equilibrium reaction for water, has no units. Anything else? The power of Ka has no units. The power of Kb have no units. So these things have no units. These are mostly used for as a scale, it's comparison. Okay, comparison. Okay, one over the other. Okay, which is more acidic? You look at orange juice or milk. Measure the pH. Okay, which is more basic? Sodium hydroxide or ammonia. Okay, you look at the Kb or you calculate its pKb. You see what I mean? So these are scales. Compare one to the other. All right, let's go now to page 9. We'll do some problems here. Okay. All right, we'll do page 9, 10, and 11, and then we'll finish it. We'll finish the rest off on Friday. All right. So if your pH is 0. Your H plus concentration is 1. Okay, how did they get that? Okay, so pH is equal to minus the log of the hydrogen ion concentration. So if they say your pH is 0, okay, how will we get to our H plus concentration? In moles over liter? Okay, we're going to do 10 to the power of minus pH. I don't know if we can even do this. Okay, so what's 10 to the power of 0? Anything to the power of 0 is 1. Okay. Okay, and like that, okay, if your pH is 0, your hydrogen ion concentration is 1 molar, what will your OH minus concentration be? Okay, remember this relationship. Okay, that's coming from the equilibrium reaction for Kw. Okay, products over reactants. Okay. Right? What is Kw here? Okay, it's not just 1 times 10 to the minus 14. It's products over reactants. So products over reactants. How come I don't put water in here? Because it's a liquid. Okay, so this is equal to the equilibrium constant, and at 25 degrees, our textbook or the literature tells us this is going to equal to 1 times 10 to the minus 14. Okay, so if your H3O plus concentration is 1 molar, then your hydroxide ion concentration is 1 times 10 to the minus 14. Okay. And then so on and so forth. Notice here as your pH goes up, okay? As your pH goes up, what happens to your hydrogen ion concentration? It goes up in the opposite direction, or in other words, it goes down. If your POH, the power of OH, goes down. Okay, how does the hydroxide ion concentration go? Okay, it goes down in the opposite direction. So these are opposites. Okay? And the only time they're equal to one another is when, they are equal to one another, and that's neutral. 1 times 10 to the minus 7 and 1 times 10 to the minus 7. Okay, so understanding the relationship between pH and the hydrogen ion concentration, so on and so forth. All right, shall we do some problems here? Okay, acid-base chemistry. Okay, let's see if you guys enjoy these types of problems. All right, calculate the pH of a nitric acid solution having an H3O plus concentration of 0.76 molar. Okay, so what do we know about nitric acid? What type of acid is it? It's not just an ordinary acid. What type of acid is it? Strong. Okay, so for a strong acid, like nitric acid, we do not have to use an ice table. Why? Okay, because it's a strong acid. What if it were a weak acid, which it is not? Okay, what if it was not a weak acid? What if it were a weak acid? My neurons are crisscrossing all the wrong ways. Okay, if this was a strong acid, which it is, we can just plug it straight to the pH equation. What if this was a weak acid? Can you plug it into the pH equation? You can't. Okay, what will you have to do? Okay, you'll have to do an ice table. Okay, an ice table. So weak acids get what? Okay, strong acids. Okay, this is what we'll do on Friday. Strong acids that you saw in that list of 6, okay, you can put into pH equation. Yeah, if it's a weak acid, it's not 100% going to H+, so we have to use an ice table to get pH. Okay, if it's a strong acid, which is those 6 that we made a list of, then you put into the pH equation to get the pH. Okay, so this is something we will do Friday and next week. And if it's a strong acid, I tell students this is a very easy situation because you just plug it in to the pH equation. And what is our pH equation? Okay, pH is equal to minus the log of the hydrogen ion concentration, H plus or H3O plus. Because it's a strong acid, just plug it in. Okay, just plug it in. Okay, how do you know it's a strong acid? Okay, we're going to know those 6. Okay, we will know those 6 acids. What are those 6 acids again? Hydrochloric acid, nitric acid, sulfuric acid, hydrobromic acid, hydroiodic acid, and perchloric acid. This is nitric acid. So minus the log of 0.76. We usually do not put units inside the log or natural log. That's a no-no. So don't put units inside log or natural log. You put the units in later. But pH has no units, so don't worry about it. And what's minus the log of 0.76? About 0.119, okay, 0.12. And that's very acidic. And this is the answer. Okay, what would the POH be? 14 minus this, right? POH would be 14 minus 0.12. All right, a pH of 0.12 corresponds to what concentration of hydrogen ion? What concentration is that? pH register as? Okay, it registers as this concentration, 0.76 moles over a liter. All right, the pH of a certain orange juice is 3.333. Calculate the hydrogen ion concentration. Okay, pH of this orange juice is 3.333. Okay, so 3.33 equals minus the log of H plus. Okay, do we know how to do this on our calculator? Okay, how will we get H plus? Okay, we'll do the anti-log. Okay, so you don't do the log, you'll do the anti-log. So on your calculator, if you do second log or shift log, okay, shift log or second log, and then because it's minus sign, the minus goes in the exponent, so minus 3.33, close those parentheses, and I'm getting 4.68 times 10 to the negative 4. Okay, what am I missing here? Okay. What's something that you need to put here? You'll need to put your units, and what are those units? Okay, what are the units of the brackets? Okay, molar, moles over liter. The OH, hydroxide ion concentration of a blood sample is 2.5 times 10 to the minus 7. What is the pH of the blood? Okay, there are several ways to solve this. I think what I'll do is I'll take the POH. Okay, let's calculate the POH, which is minus the log of the hydroxide ion concentration. I got the OH concentration, so let's do the POH, the power of the OH. The POH is minus the log of 2.5 times 10 to the minus 7. Okay, what do you guys get when you put that in your calculator? I'm getting about 6.60. That's our POH, okay, but that's not what it's asking for. It's asking for pH, okay, so how will we get the pH? What will we need to do? 14 minus 6.60, very good. And what do you guys get when you do that? Is it 7.4? Yeah, 7.4. Okay, this is our answer. Which is actually, believe it or not, a good pH of the blood. Your pH should be around 7.2 to 7.4. All right, finally, which is more acidic? A solution whose hydrogen ion concentration is 2.5 times 10 to the minus 3, or a solution with a pOH of 11.6, okay, which is more acidic. All right, so what I'll do here is I need to convert this to hydrogen ion concentration. So what I'll do is I'll calculate the pH. So there's several routes to this answer. Okay, so I'll calculate the pH, and then from the pH I'll get the hydrogen ion concentration, and then I'll compare the two. Okay, so what's the pH here of this going to be? What's 14 minus 11.6? 2.4, okay. 2.4. So what's the hydrogen ion concentration of something that has a pH of 2.4? Okay, it's going to be 10 to the power of minus 2.4. Okay. And what's 10 to the power of minus 2.4? .00398. 0.003. Let me do 0.0040 molar. Okay. All right. So which is more acidic? Something with the H plus concentration of 0.004, or something with an H plus concentration of 0.0025? Which has more H plus? I think this one does, right? More H plus. Yeah. Thank you. So this is more acidic. So on Friday, we'll start talking about getting the pH using ice tables with weak acids, but for strong acids, you can plug it into the pH equation. For strong bases, you can also plug it into the pOH equation.